I have it on my YouTube channel too. Old YouTube. Have you seen the news about Facebook and Google being in trouble?
Why?
So basically, Facebook and Google and Amazon own 70% of online shopping and publications.
Are they being investigated for antitrust?
Antitrust, yeah. And what they're trying to do is push out the other 30% and own it all. So they're going after, especially Facebook and Google, for antitrust.
I mean, that's good. They own 70%.
Yeah.
That's,
Yeah. It's a big amount.
I thought we were all about the free market in this country, right? Where do you find the study here?
I'm sorry, what? Where do you find what?
The thing that
This right here.
yeah, is that
If you go to, it goes by chapters. If you go to chapter 4, and you have blank on the lesson tab on the side, on the left side of the screen, there'll be blank lecture notes and there'll be completed lecture notes. So they both will be there. So, chapter 4. We're in chapter 4. So,
I like
does anybody have any questions about anything? Okay. So this is where we left off. This balancing chemical equations. And this is a balanced chemical equation. So you see CH4, so methane, CH4, plus 2 oxygens makes 1 carbon dioxide and 2 waters. And notice that this is balanced, so there's the same number of each atom on both sides of the equation. There's 1 carbon, it's the black one here, 1 carbon here. So 1 on the reactant side, 1 on the product side. Oxygen, there's 1, 2, 3, 4 on the reactant side, 1, 2, 3, 4 on the product side. And hydrogen, the white ones here, 1, 2, 3, 4 on the reactant side, 1, 2, 3, 4 on the product side. So same number of each type of atom on both sides of the equation. So this is how you balance equations. So the next thing I'm going to do is show you how to balance chemical equations. And the way you do this is you pick an element and then you balance it for that element, and then you do it for the next element and keep on going in an iterative process. Iterative means you take the solution, just keep on going. That's what iteration means. So we'll do this. We'll start with carbon. There's 4 carbon here. Can you see it? You're squinting. Oh,
me?
yeah.
That's just my eyes.
Okay. So 4 carbons. So we need 4 over here. The way you put 4, you put it like this in front. What you don't do, you don't put 4 there. Because putting 4 there, now you have a new compound. So it's not carbon dioxide, it's tetracarbon dioxide. So you have to keep the same compound. So 4 here, and then 4 here, and as if there was a 1 here, 4 times that is 1. Or I'm sorry, 4 times 1 is 4. So now we've balanced it for carbon. Now we can balance it for hydrogen. 10 hydrogens here. So then 5 over here, because 5 times 2 is 10. So 10 hydrogens here, 10 hydrogens here. And now we have these ratios set in, so now we have to look at the oxygens. So there are 4 times 2, or 8 oxygens there, and there are 5 oxygens here. So we have 13 oxygen. I'm just putting OX for oxygen. I know it's O, but my O's and zeros look exactly the same. And so over here then, this would be 13 halves O2. So if we have 13 oxygens over here, we have a molecule that has 2 oxygens in it. So I'm putting 13 halves because we have to multiply the whole thing by 2. I mean, yeah, it's 6.5, 6.5, whatever you want to put it, but 13 halves. And so chemistry deals with discrete mathematics, only use whole numbers. We have to multiply the whole equation by 2. So then we change colors to red. times 2, so we have 2, 13, 8, and 10. So now this is balanced. So you have the same number of each type of atom on both sides of the equation. So for carbon, 2 times 4 is 8. 8 times 1 is 8. So 8 carbons. Hydrogen, 2 times 10 is 20. 10 times 2 is 20, so 20 on both sides. Oxygen, so 8 times 2 is 16, plus 10 times 1, so 26. 13 times 2, 26. So we have the same number of each type of atom on both sides of the chemical equation, and therefore this is now balanced. So, questions on how to do this? All right, your turn. So, how many waters? And I want to know, the idea is, what's this number right there? Right before the H2O. How many waters in this balanced chemical equation? Is anyone stuck? Has no idea how to start or where to go? And then feel free to work in groups. I mean, I know we have 3 individuals on the same table. You guys cool with working by yourselves? You're welcome. You can turn around and join in the groups, or you can work alone. Whatever suits your fancy. You all right? You're staying out how much days?
Yeah.
I used to start with
So
carbon
to
here,
the
so
6 carbons on the other side,
So
but
that
not like
means
6. And
6 carbons there.
you need 13
Block that
hydrogen.
one.
What do you want to do?
So many easier one.
Probably
How about H2? So plus O2 greatest common H2. Least common number is 26. There are 2.
Mhm.
So okay. Picking elements. H2. Okay. So 2 hydrogens here. 2 hydrogens at 26. Yeah. Now oxygen.
4 times 13 is the same as 26
No,
times
but
2.
but since you've locked in that the hydrogens are 1 to 1, this is
52.
Yeah. Yeah. So we get 2. So now you have 52
Yeah,
hydrogens.
you have to multiply 4 6.
So you have 6 here. What do you go for that? 4 carbons.
Why do you have 24 carbons?
Yeah. 4 times 6. Yeah. Now you already know this is not a number. So you have to double it. So already you're going to double it because this is an even number and that's not a number. So just go ahead and do now 24 on this side, is 6 on the other side. Let's go ahead and double this and then this. Well, because you've already set the ratio that's now we have like 1 to 6 here. 4 times 2 is 7 oxygens plus 6 oxygens. So now you have 2 times 13 is 26.
Is that a 26 or 28? Okay.
Now 74 oxygens. So you have 26 hydrogens. 2
Where
times
do you
3
see
is
74
26.
oxygen?
So you need 26 here. What number needs to go 24 times 2?
24 times 2. Okay. And that's 58.
That's 48. Plus this 26
Okay.
oxygens, that gives you 74. So then how do you, so we have 74 oxygen on this side. How many oxygens are in this? 74 divided by 2 should be 37.
Why are you dividing?
24. Because you have 2.
You're dividing it by the oxygens
Yeah, so
here.
you want to find out what.
So it's got
That's oxygen is 13 here, so it's 1.
Oh.
This is 13.
37 or 32?
So this is 37 oxygen.
That's what 37.
So how many O2s do you need then? So now you have 4 C6H plus 37 O2. Yeah. Yep. Goes to 24. So then this is fraction. Multiplied by 2. Yeah.
but none of those were the answer.
How many H2 others?
Oh, 27. Okay.
Yeah.
So
It's slowly happening.
you end up
Yeah,
with
yeah.
what?
Four.
Four.
Not right now. Let it soak in.
It's 37. It's hard to see from over here.
Yeah, your sevens and your twos kind of look similar too.
I put a line through my sevens.
Yeah. But you put it in a spot that makes it look like a two.
Yeah, it looks.
At least on these finished notes.
Okay. So the 37 oxygens come from the 74 oxygens that you have divided
You have new ones. Yeah. So there's an odd number here, which is 13. And two hydrogens, you have to multiply. These are two. So you have to use
So C6,
That's one. And then you balance the oxygens, you get 37 and a half. Multiply by two again, you get
plus H2O.
So
So it has to do that.
That's the original question.
yeah, it might be easier to look at the biggest. Yeah, the one with the largest amount. So you have H13.
Well, I mean,
H2.
Okay.
So
I mean, you could also say it's balanced. It could be 4,000, 37,000, 24,000, 26,000, right? I mean, that's balanced. Right?
26.
Using the smallest amount.
But how do you know that?
Because
Yeah. Think about it a little longer.
13 times 2.
13, yeah, 13, like, you know, when you add fractions or something, you have something over something.
Yeah.
Yeah.
Something over something. These have to be the same.
Yeah.
It's the same.
So you multiply this side by 13 and this side by 2.
Yeah. So like if this side was 13, this side was 2, to get these to add.
Right on the denominator.
Yeah.
You have to
Plug it
find
away.
the least common factor.
Right, least common multiple.
Or this one, yeah.
Right, so 26 is the least common multiple.
Oh. So 0 and 1.
So now, do you multiply it
Not
by,
there yet, so now you multiply this side
Yeah.
by 2. Okay, this side is 13.
and you
So,
multiply all of the
Any
H2O by
element, I usually
13?
start with
Or
carbon.
just the H?
So 6 carbons here, so you need 6
The
carbons.
H and
So
O,
now
so
you
this
lock in
goes
a
to
1 to 6
13O.
ratio that you're supposed to.
And
Right. So now let's look at the hydrogens. 13 hydrogens here, 2 hydrogens here.
Yeah, the ox.
Right away, because this is an odd number, that's an even number. Yeah, you multiply with 2. And when you multiply by 2, now this becomes 12, right? Because this is a 1 to 6, so 12, 12. Now, so 2 times 13 is 26. So if we need 26 hydrogens, what number do we need in front of us? So now you add the oxygens. So 13 here.
13.
Yeah.
15
So oxygens and then over here. Yep, 13 oxygens. 24 plus 13. And so here, how many O2 do you need? You need
Just like
37.
so there's 12 carbons. So you multiply that by
Because
12.
there's a unit too here, like do you like Twix or Twinkies? So say you need 37 Twix. How many bags of Twix do you need? You need 37 divided by 2, right? Because there's 2 in each. That would be 18 and a half, right? That would be 18. If I want 37 Twix, I would need 18 and a half.
Okay, tack down the oxygens,
Right, so the 18 and a half is 37 over 2. But the point is, we can't have that fraction. So you multiply the whole thing by 2.
13 plus.
Multiply everything by 2, so this becomes 4,
Yeah,
37, 24,
Oxygen
26.
plus
24.
Now-
And it's definitely not 70, it's like 50.
13 plus.
Oh, is that what
24 is 37.
Oh, yeah, I thought it was right up here.
37.
Okay, I'm sorry. No, you're doing fine.
37 oxygen.
Oh, jeez.
So you need to do, so if you did that,
Or no, the one I can't see is two.
Starts 37 over 2.
Yeah.
Or balance it.
So now we have 37 over 2.
Yeah.
And then we have to multiply the whole thing to get rid of that fraction.
Yeah, so now all of it by 2 to get rid of that.
Okay. Okay, so
I guess for, so that last time we went to.
alright, so you're as far as here. So you know how many oxygens are here? 2.
Do you keep that
Oh, you're
O2?
at 6. I thought you were going to yeah. So how many oxygens? No, it's 12 times 2. 24 oxygens. Yeah.
Oh.
Yeah.
Let's do it one more time.
So this is 37.
So C6,
So how many
H13,
of these do you rest?
O2,
You need 37 divided by 2.
H2 plus H2O.
Yeah, that is. Yeah, basically, yeah. Yeah, the problem is, yeah, it's just, this is 37 oxygen. You have to start with the weird, you have to divide by.
This is so hard.
Because it's two
Okay, so what you're gonna do is you're gonna please
So
divide
what do you do now,
So
since you have a half
you
here?
multiply
You
this
multiply
by
the whole thing
13
by
and this by 2. So
And
now
then
you have your 2
you can do so multiply by
C6
2,
H13 plus O2
Yeah.
CO2 plus
Yeah.
13 H2O. And then you did the carbon second. So this is 12.
So this becomes 13. Obviously, you're choosing 12.
So 2 times 6 H13
You guys
plus
do it.
O2. 12.
So then
Oh,
C2
you have,
Yeah.
Oh,
I have 4.
yeah, so next third is oxygen.
I don't know if making you feel bad or talking about that one.
Oh, I feel bad.
Oh,
Yeah.
so that's how you're moving.
This one by oxygen. That's this one.
Yes.
And then oxygen is there's 13
But this
oxygen,
is basically.
15 oxygen.
Okay, that makes more sense.
Oh shit.
So 24
You don't have to see the
37.
notebook there. I couldn't see the notebook over there.
What happened?
Are you, I mean,
30s.
I don't know if you're having a hard time reading.
No,
It's
I'm
hard.
just having a hard time like understanding how
And
it
to get rid of
works.
Yeah.
fraction.
But I'm getting there. I've done it probably 3 times now.
Did you get it right?
Yeah, we get it right every time, but it's just repeating the steps to get it right, which helps me. So,
It's not so much like.
Okay, that helps. I was just doing the front numbers.
Yeah.
So 13 oxygen plus another 24 oxygen.
Yeah,
So
because
there's
you have
12 times 2 here,
total
24 just on this one, and then 13,
so total you have 37.
37 oxygen on that side, which is
You
how
have 2 over on this side.
All right, I'll give you an easy one.
I'll just write it
You balance this.
you just, it would be 2H,
You got the 12, 12.9.
You can.
so you just have to multiply those two, yeah.
Oh, sorry, I got 2.
But now you have 4 oxygen, or
Now you have
4
2
hydrogen.
oxygen.
You have 2 oxygen.
2 oxygen and 4 hydrogens, so you have to put another 2
Yeah.
here.
That's it,
Okay,
right? So what you did is you locked in one element. Right? You look at the oxygen, there's 2 oxygens here, so you need 2 oxygens here, but now you look at the hydrogens, now you've locked this into being 2, this to a 1-to-2 ratio. Now, like, oh, okay, this needs to be a 1-to-1, 2-to-2 ratio.
okay,
Right? So
So-
it's just locking in the ratios.
I agree. And then when we, so how can we divide here, get 37? Because there's 37
on this side.
oxygen total on
Yeah.
this side.
Okay, look at the green numbers, right? So the green numbers, you have 2 C6H13,
Mm-hmm.
and then that forces you to have 12 CO2s. Right?
We're at 12 CO2s, yeah.
and 13 waters. So, and so if you, well, let me back up. So to get here, you have a 1:6 ratio here because there's 6 CO2s there. Now you have an odd number here, and there's an even number here. So you have to multiply by 2 to get rid of to get them both even.
Yeah, to get rid of the 2.
Yeah, no, we're not even at the oxygen yet.
Oh,
So multiplying these by 2, you need 12 CO2s and 13 waters. Now now you've locked in the ratio between here and here and here and here. Now the last one left is oxygen. The ratios. So 12 times 2 is 24 oxygens. 13 times 1 is 13 oxygens. And together is 37.
mm-hmm.
Right? So 37. So because this has a 2 in it.
Mm-hmm.
Like you like Twix or Twinkies or anything like that? Twix. And that comes packed 2, right?
Yes.
So if you need 37 Twixes, how many packets do you have to buy? 18 and a half.
Wouldn't it be an odd number?
Yeah. But if you need an even, but I mean, the point is that when you buy Twix, you can only buy them in packs of 2.
Uh-huh.
You can't buy single ones.
Uh-huh.
So when you're looking at whole numbers of thing, you have to multiply the whole thing by 2. So you need 37 halves or 18 and a half to get 37 Twix. So then you have to multiply the whole thing by 2. You get a 4 to 37 to 24 to 26 ratio.
So what if it was a 3? Would you multiply the
Yeah.
whole thing by 3 then?
Yep.
So you multiply it by whatever's in the
If it was like
denominator.
03, it'd be 37 over 3.
Yeah.
And then you would multiply everything by 3.
Yeah.
Okay, so you cancel that out.
Yeah.
Okay.
Should have spread for this larger one.
Mine is not working and I'm very concerned.
It's like $300.
Is that part of that?
I don't know. School bought it.
Oh, perks of being a teacher. Lord.
Bought with family money.
At least something's flat. Productively.
I mostly used to watch Netflix though on airplanes.
Yep.
No.
So, 37 to
That would be much easier to draw.
How come you can't just multiply? So you know how you just put the 12 in front of everything else like that? Why can't you just put a 37 in
I
front
mean,
of it?
if you
Because
you-
you need to have 70.
no, I mean it's however you want to balance it. I mean, it's
Oh yeah,
oxygen,
because
you
you
don't
would
wanna
have
start off-
70.
oxygen's hard to start off with because you have 2 unknowns. So like when you solve systems of equations, you have to have the number of equations of equal to the number of unknowns. You have 1 unknown and you have 2 possible equations. So actually, you try and get the ratio between oxygen and these 2. You have an infinite solution set. So you have to solidify. You can only solve for oxygen after you get everything else cemented in terms of ratios.
Mm.
So does that make sense?
Yeah. So you don't start with oxygen ever, or just in this?
Just in this case, because there's oxygen here and oxygen here.
Mhm.
Just look for like the easiest thing to get first.
Those are called degrees of freedom. So right here between this carbon and this molecule, there's 1 degree of freedom. So meaning that there's always going to be a 1:6 ratio between these 2.
Because
And why is
there's
there a
only-
1 to 6 ratio?
Because
Because
there's
there's
6
1 carbon
carbons.
there
Yeah.
and 6 carbons
Yeah.
there.
Yeah, and carbon's only found there.
Okay.
And the ratio between here and here, it's going to be a 13/2, a 2 to 13, whatever. A 2 to 13 ratio, always, because there's 26 hydrogens.
And there's 1 oxygen on this side and oxygen in both of these. So
Yeah.
that's,
So you can't determine the ratio. You can't start off with oxygen because the ratio here is actually there's an infinite solution set. I mean, let's ignore everything else. Let's just say oxygen. You could have 2 O2s, 1 carbon dioxide, 2 waters. That's good. That's a solution. You could have 4 waters, 1 CO2, and 3 oxygens.
Mhm.
I mean, so because of that, there are several solutions, but if you lock these down first, there's only 1 solution.
You can't mess with the balancing of the carbon and hydrogen.
Yeah.
Okay. Hmm.
yeah, this took me a while to get down in high school.
I've never
It's coming
taken a
back.
chemistry class
It's coming back.
before in my life.
Well, good. You have 20 minutes to master it.
Yeah, right. I'm so far behind, I feel like, when it comes to stuff like this.
Do you have any other questions?
No.
I checked the last week. How you guys doing? You were talking, so I skipped over you. You guys talking? What?
Okay, so figured out how to
You can
handle
look
it.
right here. But you can look there. Are you?
So I got this and this. Let's add up. Then the 37 up to 2. Then
Why multiply by 2?
no, I understand why you multiply it by 2 so you get the fraction out of it. But then you end up with 37 and then the 37.
Well, I mean, I just wrote under it. I can erase these. It's going to be 4, 37, 24.
No. I got the 37 part.
Okay. Also,
Oh, okay. Never mind. I'm good.
37 hours first.
Yeah, the 37 was the most confusing part, but I got that. I figured out exactly it.
Yeah.
You also when you're doing with these numbers, you don't mess with. If you're multiplying the whole thing by 2, you don't. These you don't.
No,
These, no, you don't just don't touch those.
Yeah. That's it. Alright.
Figure that out.
Basically, at the end of the day, you want to just
Alright, so, oh, the internet's fast today for a change. Alright, so we're at 26. Got around everybody. Anybody have any questions though? No.
Oh, that's right, okay.
Alright, let's get away to something happy, like a happy meal. You guys like Happy Meals? I don't. Well, what's in a Happy Meal?
Apple slices.
Apples,
Small fries.
fries. Anything else?
10-piece chicken nugget.
Okay.
A toy.
4 or 6 pieces.
Toy
Oh.
and I think I mean it's been a while since I had one. I think maybe this is like the nuggets. And then drink, right?
Milk. Yeah.
Right? Okay. So let's say I've got 1,000 units of 5-piece chicken nuggets, 1,000 fries, 1,000 toys, and 10 milks. How many Happy Meals can I make with these? 10. Why can I only make 10?
Because you only have 10 milk.
Yeah, because I'm limited by something, right? The whole idea, I'm limited by something. I have excess of all these, but since I only have 10 milks, I can only make 10 Happy Meals, right? So, oh, yours, Barbara. Okay. No, you're fine. I see hands go up. I'm like, oh my gosh, questions. And the point why I'm doing this is chemical reactions work the same way. They progress until they're limited by something. So chemical reactions will go until they run out of something, and then they won't go anymore. And that thing that we run out, we call it the limiting reagent. And chemical reactions can be a little more complicated though, because they can have more than one ratio. So like a ham sandwich, so a simple ham sandwich, 2 slices of bread plus 1 slice of ham makes a ham sandwich. So if I have 1,000 pieces of bread, 1,000 slices of ham, how many ham sandwiches can I make?
500.
Yeah, 500. Because and what's limiting here is the bread. Oh, that took a while to show. What's limiting is the bread, right? Because there's 2 slices of bread to 1 ham sandwich. So because of that, we can only make this number divided by 2. So in this case, we're limited by the ham, and then we would have, limited by the bread, plus we have another excess hams. So we have one thing we're limited by, and then we're having excess of something else. So let's talk about this with a problem. And this is an easy case. This is a limiting reagent problem, but it's where one limiting reagent is in such excess, you already know what the limiting reagent is. It's kind of like driving your car. When you drive your car, you're worried about when you're going to run out of fuel. You're not worried about running out of oxygen. I mean, you are if you are driving a car in space, if you will, but here on Earth, there's just so much oxygen in the atmosphere, you don't worry about, oh gee, am I going to run out of oxygen when I go to Hana this weekend? No, you're going to run out of fuel. So this equation here, problem. So during photosynthesis, plants convert carbon dioxide and water to glucose according to this reaction. Glucose is C6H12O6. So 6 carbon dioxides plus 6 waters makes 6 oxygens and glucose. So this is a photosynthesis reaction. And a plant consumes 37.8 grams of CO2 in 1 week. Assuming that there is more than enough water present to react with all the CO2, what mass in glucose in grams can the plant synthesize from CO2? So problem solving, let me highlight in blue what we're looking for. What we're looking for is what mass in glucose. Actually, I'll just put this. Mass of glucose in grams. So that's what we need. Mass of glucose in grams. What's the given information? We're given a balanced chemical equation and an amount of reactant. And what do we not care about? The 1 week. Time's not really a matter here. Doesn't really matter time. So we have to get from the given information, 37.8 grams of glucose, grams of CO2 to mass of glucose on the other side. And we do it with dimensional analysis. So meaning we're going to start with 37.8 grams of CO2. And then on this side needs to be grams of glucose. So how do we do this? Well, hopefully I'm training you guys to think, when you see mass, what's the moles? So we need moles of CO2 and the molecular weight of CO2. So, and of course, we'll do a periodic table. Carbon is 12, and oxygen is 16. So 14 plus 16 times 2 is 44. So it's 44. Carbon's 12.01, so it's really 44.01, but 44 grams CO2. And now this is a new step. The new step is here. We need, for every mole in GLU, that's shorthand for glucose. So if you ever see someone write GLU, that means glucose. Mole glucose over 6 moles CO2. So this is a new step. So, and you get this from the balanced chemical equation, because there is for every 1 mole of glucose, it requires 6 moles of CO2. So this is where the 1:6 ratio comes from. And the last step is to convert to grams. And we had in the previous problem 180 grams of glucose to mole of glucose. And you can see they all cross cancel. Right? So gram CO2 cancels, mole CO2 cancels, moles of glucose cancel, and we're left with grams of glucose. And so you multiply the numbers on the top, you divide the numbers on the bottom. So 37.8 divided by 44 divided by 6 times 180, and you get 25.8. So this equals 25.8 grams glucose. And that's our answer. Okay. Recap for this one. We're given photosynthesis reaction. A plant consumes 37.8 grams of CO2. How much glucose is that going to make? Well, you start off with your given information, and the given information is the equation and the mass of glucose. And now we have to convert to moles. So we're going to eventually get to mass of glucose in grams. So let's convert to moles. New step, look at the ratio between the glucose and the CO2. And this information you get from the balanced chemical equation. If the chemical equation is not balanced properly, you will get the wrong answer. And then molecular weight of glucose, and looking at and then doing the analysis, we get 25.8 grams of glucose. Yeah, thanks.
So that 6 mole CO2 comes from the first 6 CO2.
Yeah, 6 CO2, and nothing there, so it's 1.
So if it was like 8 CO2 or 7
Yeah.
CO2, then it would be 7 mole CO2.
Yes. If it was 7 and 2, that would be 7, that would be 2. Right, so.
Because on the other side there's no 6 in front of it.
Okay, this is hypothetical. Hypothetical,
Okay.
random hypothetical. If this was 7 and this was 2, this would be 2 over 7. Or my 2's look the same? I'll make it 3.
No, this isn't.
3, like that. Oh, no, okay. So, the question for this? Okay, so this is probably algae, and they we've done a lot of experiments with this. We actually, well, we talked about carbon credits last class. It was proposed to have $30 per ton CO2. It's a carbon credit. And there were a lot of research pumped into seeing how much plants absorb CO2. And so this is the type of experiment they would do. It's interesting for a couple of reasons. First of all, they found out that that United States outperforms everybody in terms of our cropland. So like when they did the experiments here in the United States and then they tried to reproduce them in like Ireland, it was like, no, we cannot compete with the United States. And the reason why we had to thank that is actually Canada. So the United States, we have very, very productive cropland, especially around Ohio, Indiana, Illinois, and Iowa. That's just it's the best in the world, really. And I say we thank Canada because about every 100,000 years, we go through a cycle of about 90,000 years of ice age and 10,000 years of interglacial. So right now, we're in an interglacial called the Holocene. And there's an ice age coming. We don't know when. We've been in a long interglacial. It's been about 11,500 years since the last ice age. So we're due for another ice age. But it doesn't mean it's going to happen tomorrow.
Be nice.
I don't want an ice age.
Compared to this right now, maybe.
Okay.
I enjoy the tan, personally.
Well, I guess Hawaii would be very pleasant because we're in the tropics. But what happens in the ice age is the glaciers come and then they scrape all the topsoil off of Canada and they plop it down in the United States, or the area that is the United States. And this has happened like tens of times for the past couple million years. And so because of that, we just have this amazing topsoil in the United States. And it can't compete, no one else can compete with us in terms of our crop productivity. And we generate a lot of food here in the United States. Maybe not so much in Hawaii. Actually, here in Maui, we only make 13% of our food. Very small amount.
What's the next country that makes the most food? China?
It could be China. I guess it wouldn't be Russia. Their population isn't that big. It's going to be around the same latitude. It's either going to be Ukraine is pretty big too. Ukraine is big, China's big, and then on the other side, Australia and.
Picturing the map.
Yeah. Okay. I guess China's pretty big. It's these latitudes. So it's going to be United States. So it'll be through here, Ukraine. Because Ukraine is all right. Well, Kiev is here, so that's higher up. Yeah, it's China. But if you look, there's a lot of steppe here, and I'm not sure. I don't know the food production in China. It's got to be a lot. and then the bottom part here. So around Argentina, South Africa, and Australia.
So like the tropics would be too hot to produce too much food, or?
Depends on what type of food you're trying to produce.
It's cereal grains. It's the food that's more useful is the storable kind. So I mean, you can grow. I mean, by biomass, I mean the Amazon's full of biomass, but I mean you can't really eat tree bark, right? So it's not just biomass; it's a type of crops, and specifically it's cereal grains. I mean, we make lots of papayas here, but papayas only last a couple of months, whereas corn and wheat can last for years. So, in terms of agriculture, by agriculturally speaking, and population and feeding the population, sustainable population, those bands around where the United States is, or continental U.S. is much more valuable cropland. That's also, I'm stealing that concept from a book called Guns, Germs, and Steel. Yeah. Okay, so, specifically algae. Algae is interesting. So Al Gore wanted to have the carbon credits because he wanted to dump iron into and around Antarctica, and that would cause an algal bloom. There's not a whole lot there, so it probably wouldn't affect the ecosystem that much. So then you can sell that as carbon credits. And algae is interesting because algae grows until it's limited by something. Same thing, but algae is just a single-celled organism. So it divides. So it grows very quickly. So compared to corn, say you're growing corn, there's a lot of energy that goes into growing corn, at least the corn plant itself. It has to grow roots, it has to grow a stalk, it has to grow leaves, and finally it grows the fruit. So it takes a lot of energy to get up to harvesting the corn, whereas algae is just divide, single cell. And so we're looking into algae also in terms of space travel. So if we're going to colonize Mars or be long-term on the moon, we have to grow our own food. How are we going to grow our own food? It's very likely going to be algae. And we've genetically modified algae that we can get it to produce proteins, fats, and carbohydrates in large amounts. We have one that generates a lot of fat, and one that generates a lot of protein, one that generates a lot of carbohydrates. And they already use it in baby formula. So a lot of the fats found in baby formula, the omega-3 fatty acids, you can get them other places. You can get them in walnuts, for instance. You can get them in fish. But where we generally get them now for the baby formula is from algae. So have you ever seen The Martian, the movie, or read the book? The book is hilarious, by the way. If you have or have not, he wrote another book, Anthony Weir. It was called Artemis. It's after The Martian. It's not as good as The Martian, but it's about colonizing the moon, and they all ate algae. So Anthony Weir, he does a good job. He's a kind of a practical science fiction writer, if you will. So they all ate algae, and they called it gunk. So that's what they primarily ate there was gunk, just algae. So that's interesting. So we'll look at that for space travel. Also with algae, there's a form of pollution called eutrophication. Have you heard of that word before?
Mm-hmm.
Eutrophication is when you add nutrients to the environment. And then what happens when you add nutrients to the environment, you get an algal bloom. And depending on where you're at, the type of nutrient that you add will create certain algal bloom. And different species also, it depends on the species. So here in Hawaii, it's a problem with the phosphates because they grow on the coral reefs. So, and the phosphates, they come from us. It comes from our urine. Because we just dump our waste right in the ocean, really, to be honest with you. And but in other places, in the United States, Mississippi River Valley, the limiting nutrient is phosphorus. So just like here. And we used to use phosphate detergents in the United States, and they were these huge algal blooms in the Mississippi River, and that was choking out all the life. So they stopped using phosphates, and that problem has kind of gone away a little bit. But if you look to the Gulf of Mexico, the limiting nutrient there is nitrogen. And then when the spring runoffs come, a lot of times you'll get algal blooms in the Gulf of Mexico from the cropland, from the water rushing down from the cropland. And but this happens naturally as well. So around Alaska, there's really shallow ocean, and the limiting nutrient for the algae around Alaska is sulfur. So when the seasons change, the oceans, there's churning of water in the bottom of the ocean, and sulfur comes up from the bottom of the ocean, and then you get a huge algal bloom around Alaska. And that huge algal bloom will then support populations of krill and other bait fish. And what happens? Well, the humpback whales that are here in Hawaii, they migrate up to Alaska, and they gorge themselves on all the krill, and then they come back down here. So, and not only that, even more so, the algae, that's where we get our oxygen from. So the oxygen in the atmosphere is not significantly from trees. So around 3/4 of the oxygen in the atmosphere is from algae. So it's not really from terrestrial-based plants. I mean, some of it is. You know, a little less than a quarter is from terrestrial-based plants, but most of it is algae, vast majority. So that's what really, in my opinion, that's what really rules the planet is algae. So, I mean, I know the issue right now in the Amazon burning, that's scary. It's bad for the diversity, but it's not going to affect the oxygen producing capacity of the planet by very much.
But it is destroying a large carbon sink, right?
Yeah.
More carbons.
Yeah, it is. Yeah.
It
And,
sucks.
Yeah.
Yeah, let's not play it off, it sucks.
I mean, I'm not saying like, yay, let's burn more Amazon. That's not my point. My point is that oxygen really comes from algae. And algae is a very important plant and will be an important plant in the future. It's interesting, I talked about some of the think tank stuff. The future of food, we think it's going to change with space travel. Also the future of jobs, I already talked about that, but with 3D printing, that we might be using 3D printers to make food.
Nice.
So, I mean, your hamburgers, we can have a hamburger that's 3D printed, and what's the input going to be? I mean, you can go and get, Safeway Select insect-based stuff, or you can go to Kirkland and get the organic or something, or maybe algae, like before we get there. We'll have algae-based stuff. There'll be the feeds for our 3D printers, and then that's how we'll eat food. And people will look at us longingly. Hey, you guys are the ones that actually ate real plants and animals, not the stuff that 3D printed. So we'll see. Interesting seeing where the world will go. Okay. So now we're going to go on and talk about limiting reagent as well. So let's look at this equation here. So we have, and this is actually how we make ammonia. Usually in the book there's some kind of weird examples, but this one is in fact how we make ammonia, and you make it over an iron catalyst. So nitrogen that we get from the air, those 3 hydrogens makes ammonia, 2 ammonias. And this was discovered in and around the year 1920, or maybe a little before, 1915. We started being able to make ammonia in mass quantities. So this is important because around the year 1900, the world's population was about 2 billion. And now the world's population is around 8 billion. So we doubled twice in about 100 years. If you compare that before, we were about 1 billion, maybe about the time of the Roman Empire, maybe a little before. So it took us 2,000 years to double, and then it took us about 100 years to double twice. So obviously something has happened between the year 1900 and present day, and one of the reasons for the huge population growth is the industrialization of our agriculture. So we get lots and lots more food. That's number one. Can anyone guess what the number 2 reason is from the
Drugs.
drug? Yes. What kind?
Ecstasy.
No.
Oh.
Ecstasy is not
Sorry.
why there's a huge population boom.
Well, you think sex on ecstasy is like the best.
Oh,
No, no.
okay, well I like your thinking, but let's,
Psychedelics.
antibiotics.
Oh. That too.
Antibiotics, because
Where your head's at, though.
because if you look at the reason why people died, so before the 1920s. Why did people die? Well, pneumonia, septic shock, whatever, sepsis. So, I mean, disease, specifically bacterial-based diseases, are what killed people. And how do people die now? What are the deaths caused?
Bankruptcy?
And
Really?
suicides that are like
Suicide,
increasing rate.
suicide for our age.
Yeah.
So our age, the deaths are caused by accidents or murder or suicide.
Yeah.
But people do die of disease at our age, but it's not as frequent. Well, what about old people? How do most people that, I mean, the average life expectancy is in the upper 70s.
Heart
Over
failure, cancer.
heart failure, cancer, so cardiovascular. Alzheimer's tends not to kill people; it just incapacitates them. So, like, you don't die of AIDS, you die of a cold or disease, right? So, but yeah, the big killers today is cardiovascular and cancer, slow deaths, so very old age kind of thing. So it's changed the way we live, changed the way we die through science, really. And but let's go back to the year 1900. The leaders of the world knew there was a problem because we were facing what's called a Malthusian catastrophe. Have you ever heard of a Malthusian catastrophe before? That's when your supplies run out, specifically due to the supply being, in most cases, food. Supply growing arithmetically, and then population grows geometrically. So what I mean by, like, say I can get 50 bushels of corn from an acre of corn. So if I plant 2 acres, I get 100. If I plant 3 acres, I get 150, right? So the growth is arithmetic. So if I want to double my production, I have to double my crops. So population grows geometrically. So if you look at my family, so
Geometrically or exponentially?
same thing.
Really?
Yeah.
I've never heard
Geometric growth is exponential growth.
I've never heard that. That's
Yeah. So if you look at my own family, my mother, she's one of 8, and I'm one of 5, and I have 27 cousins on my mother's side.
Oh God, I think you're gonna say kids.
And no, I've got 0.
Smart. Environmentally friendly
And-
of you.
And maybe in the future I'll have more. I don't know. We'll see. But I also have 11 nieces and nephews within my immediate family. I'm the only one that hasn't produced. So of the 5, I'm the least productive at 0. So you can see, right? You go from 2 to 8 to 27 to God knows how many is the next generation, right? So that's geometric growth. So my dad's side of the family, though, he's one of 2, and his brother has 1 kid, and I guess they have 2 daughters. So I guess you become count as both. Though there's 13 on our side, you count both of them. But anyways, either way, populations can explode quickly, very quickly. And how do you feed that population? And what we were doing at the time, around the year 1900, we were mining. We knew it was nitrogen that we need specifically. We were mining nitrates in Chile. So guano and nitrates in Chile was supporting the crops. But the leaders were like, this is not sustainable. If this runs out, if we can't find more nitrates, a lot of people are going to go hungry, and it's going to be a big war. Germany came around. Germany figured out the Haber-Bosch process. So actually, I think Karl Bosch is more to blame, or not more to blame, to be exalted than Haber. But that's my own personal opinion. Karl Bosch figured this out, and he found out that if you took iron from Sweden and you heated it up in the presence of hydrogen for 8 hours, it made a good catalyst. How he figured that out, I have no idea. He was trying just a bunch of random stuff. Why he decided to heat it up in a hydrogen. But we figured out that was in the 1920s, the teens and 20s. In 1970, we figured out that the hydrogen got rid of sulfur, and that Swedish ore had potassium and aluminum in it that made it better for a catalyst. So we can make our own catalyst now. And that's still the catalyst we used. We use today to make ammonia. And if you know your history, a couple things happened because of this. Right after Germany figured out they could make ammonia, they invaded Prussia. I mean, I know the murder of Archduke Ferdinand maybe is the thing that set off World War I, but I mean, what allowed Germany to fight was the fact that they made their own, they made ammonia. Because you can burn ammonia and oxygen to make nitrogen oxides and add water to it to form nitric acid. So, so you can make explosives from that. So TNT, anybody know what TNT stands for?
Dynamite.
No. Toluene. Trinitrotoluene. Do you know what's in dynamite?
Time nitro.
No. Nitroglycerin. How do you make nitroglycerin? Take glycerin and nitric acid.
Okay.
Like Fight Club. You've seen Fight Club.
I don't remember it. I've seen it,
Yeah.
but I don't remember it.
So you hear the words nitro a lot, right? Trinitrotoluene, TNT, nitroglycerin. You know, so nitric acid can be used to make explosives. And ammonium nitrate, that's the fertilizer you can use for a bomb. So you can take nitrogen and you can turn it into a fertilizer, which is the reason why we have such a huge population, good or bad. But you can also make explosives, and that's really why Germany, among other reasons how Germany could fight World War I, was because of that. Because the British, they had a huge navy, they had the best navy at the time, and they're like, this is an easy war. We're just going to blockade the Germans, and they won't get any nitrates from Chile. They won't be able to make explosives, and their people will starve, and this will be, you know, we'll just kind of make sure they don't get too far with their trenches. And nope, they kept on making explosives, they kept on feeding their people. And also, if you know your history, Sweden was neutral in World War II.
I love Sweden.
What's that?
I love Sweden.
That's a nice place. A bit like Wisconsin, I think. But but Sweden brokered a deal with Hitler, so they reached an understanding that Sweden would continue to apply the Third Reich with iron ore, and because they needed the iron ore to make tanks and also for ammonia, and Hitler would invade them, so they were neutral. But I mean, they weren't really neutral; they're actually kind of on the side of Nazis, to be honest.
Oh shit.
Yeah, but we don't really.
Modern day Sweden. Love modern day Sweden.
Well, I mean, Italy was on the side of the Nazis too, but people seem to forget that.
I don't like Italy. It's overpriced.
Go to Croatia. Okay, so my point among other things is that chemistry is important to history. It's also important to politics. Can you imagine if someone said, "Oh, hi, I'm an Iranian student and I'm studying nuclear physics"? You know, do you think that student would stay in the United States for long?
No.
Right. So, okay. So, but let me go back and talk about this. So, 1 part nitrogen to 3 part hydrogens to 2 part ammonia. And we have this vessel here. So let me see here. This is N2 plus 3H2 yields 2 NH3s. So what's going to happen? What's the limiting reagent? So let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 hydrogens. I'll put an 8 here. And there are 2 nitrogens. So this is a case where we don't know what the limiting reagent is, but it's nice because it's a small number. So 2 nitrogens, if we have them react all the way, will form 4 ammonias. And 8 hydrogens reacted all the way will form, and the ratio would be 2/3. So it would be 20, wait, that doesn't make sense. So we could form from the NH3, let's see here, I guess it would have to be 6, it could only be 2. But I guess this is a nice case where you can only make this many. 16, wait, 16 divided by 3. That'd be 5. Okay, so from this you could make up to 5 ammonias from these 8, because 8 of these means there's 16 hydrogen atoms, and you need 3 in that to be 16/3 or 5 1/3. So you can make 5. So what's the limiting reagent? You can make 4 with nitrogen, you can make 5 with hydrogen. Nitrogen. Nitrogen's a limiting reagent. So, but this case, it's close. And if you can only make 4 ammonias, that means you're going to have 2 hydrogens left over, because making 4 of those is going to consume 6 hydrogens. And say which of these reaction vessels is correct. This one here, this reaction has not gone to completion. There's still unreacted reactant. Here, there's 4 ammonias. It doesn't have the X reactants. Here, there's 4 ammonias and 2 hydrogens left over. This one here is what it would be end after it runs to completion. So, questions of this? Okay, so next thing we're going to do is talk about limiting reagent theoretical yield. So what is the theoretical yield? It's the most that you can get. So the most you could possibly get from something. And looking at this, we don't know. And this says ammonia can be made by this reaction. So 2NO plus 5H2 makes 2 NH3s and 2 H2Os. So starting with 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen, what is the theoretical yield? So let me write this and you can see it a little better, and I'll zoom in on it. Okay. So I tried to translate what's on the thing there so you can zoom in so it's easier for you to follow. So we have this balanced equation. We start off with 86.3 grams of nitrogen monoxide, 25.6 grams of hydrogen, and what's the theoretical yield? What is the most we can get from this? Well, the way you solve this, I mean, looking at this is not something where it's obvious. So you have to solve it twice. And then you look at ammonia, and you pick the value that's the lowest. So do you pick the greater or lower one? You pick the lowest one because it's a limiting reagent. It's the one that will make the least of it. So let me show you. Okay, so nitrogen monoxide, so think in moles. Nitrogen is 14. Again, you'll get the periodic table. You don't have to memorize it like I do. 14 grams per mole for nitrogen, 16 grams per mole for oxygen. So a mole of nitrogen monoxide is 30 grams. So, and then the next thing to look at the stoichiometric ratios. So it's 2 moles ammonia to 2 moles nitrogen monoxide. I'm writing 2 just because it's on the equation. You can write it, you can just do it 1-to-1 if you want. And then ammonia, so nitrogen is 14, hydrogen is 3. 14 plus 3 times 1 is 17. 17 grams ammonia per mole ammonia. And then you have to do it twice. So meaning if you look at the hydrogen, same thing. Mole H2 to 2 grams H2. Then you have 2 mole ammonia to 5 mole H2, then 17 grams ammonia per mole. Okay, so notice the equation though. This is 2 to 2 here, and 5 to 2 here. So this is a different ratio. Does that look like not a 5 or? And then you have to calculate it twice, so let me calculate it for you. So 86.3 divided by 30 times 17. And this is 48.9. And this is grams NH3. I'm running out of space. So then we have 25.6 divided by 5 times 17. This is 87. Okay, so we have This one, where we can only form 48.9 grams ammonia, and this one here will can form 87 grams of ammonia. Which one do we pick? The smaller one. So the idea of limiting reagents, we have to pick the one that has a smaller value, because that's the whole idea. We are limited by something. In this case, it's the nitrogen monoxide is the limiting reagent. So that is our theoretical yield. And we will get into next class that's about actual yield, but we'll talk about that later. Okay, so recap for this one. We have this equation, these starting materials, and we have to figure out what the limiting reagent is and what the theoretical yield is. So we convert to moles, convert both to moles, then we look at the balance equation, get the stoichiometric ratios, and then we convert back to grams of ammonia. We find out that nitrogen monoxide is a limiting reagent because that's the lowest amount, and we can get, with this equation, 48.9 grams of ammonia. So, questions with this? Yeah.
On your finished notes, there's like a 2.88 and a 5.07. Where do they fall into this equation?
The book does it. I copied what was in the book in that one.
Okay.
That stops here.
Okay.
The book stops here, and then they converted the number of moles, and then with the number of moles, and then the next step is multiplied by 17.
So they just saw that it was 2.88 moles,
Yeah.
and then just knew and just stopped there.
Yeah.
Okay.
Does it matter if it's moles or grams?
No. Same thing, really. I mean, when I was making the videos, I didn't want to pause the videos and write in my calculator, so I really just went with the book said. Because otherwise I have to pause it, and then you hear it blip in the matrix when you start it again, and then I forget what I was saying, and anyways. All right. Other questions? All right. Here's your turn. 100 grams of oxygen, 100 grams of hydrogen react. How much water will form? Or if you really like, we can just, because this is actually also where we ended last class. I mean, but we got 5 minutes. A little cement in your head. Okay, so some hints. The chemical equation is 2H2 plus O2 yields 2 waters. And also O2 is 32 grams per mole. H2 is 2 grams per mole. That's an ugly mole. Both ugly moles. And water is 18 grams per mole. So how do you start? You're going to start with 100 grams O2, 100 grams H2. And you'll just keep on creeping down till you get to grams of water.
Oh, wait, we just do that. Where did that come from? So it's O2H2 and 2H2O.
You ever play trivia at the establishments? You guys ever play trivia? You get hints? Oh, you've never done that? Oh, they don't do it here? Oh, well, I'm giving you hints.
So that 112.12, is that in grams or moles or moles per gram?
Okay, now you're keeping this for
This is for O2, this is for
Mhm.
O2 here.
So you gotta double
So
add.
it's O2.
No, I am doing O2.
And then it's 2 grams H2 because that's hydrogen's atomic mass times 2.
Yes.
Because you're going from moles to moles water. So it's gonna be. So for oxygen, it's gonna be 1 to 2.
And 18 is the atomic mass of H2.
See how it's basically a 1-to-1 or 2-to-2 ratio of
But you look at the units.
of purity.
You look at the units.
And then 2
This cancels.
Wow.
because then you have 4 H's and 4 H's in this.
Yeah. And then the
4 H's and 4 H's.
Okay, so how's that a 1-to-1 ratio?
2-to-2 is the same thing as 1-to-1.
So could it be mole H2 over mole H2?
2 moles of H2 over 2
Oh.
moles of H2.
But it's not, it's mole H2O over mole H2.
You're going to.
Because they simplify 2 H2.
Yeah.
And it's a 2-to-2 ratio because of the 2 hydrogen.
But it's also ratio.
But why do you need the 2 then?
It's 2
Just
moles
so
of
you
H2.
can just-
Oh, this is then you see 1 mole into this ratio because it's 1 to 2 here. It's H2. And H2 is 2.
Oh, okay, and it's not balanced because
And
there's
this is
no
a
2.
2-1, but
Oh.
it is now.
But now it is, yeah, but had I not, okay.
That's right.
So it's just
And the question is how much H2O will form, and since this is the smallest number left in the day, is your answer?
yeah, we're about 2 minutes left.
My head can't take it anymore, and this is all.
Alright, so we
I'm
can-
doing
yeah.
library.
We can pick up here on Monday.
Maybe a library. I believe it's yours.
That's assuming.
And then you can do.
So that would be.
This is gonna sound really terrible of me, but is there a McDonald's around here somewhere?
Yeah.
Can we go? I'm craving a McDonald's.
Thank you.
Huh? I know, well, yes, but I'm also
Or
starving,
either-
and I need like a little bit of a break from all of this nonsense.
Oh, yeah.
So this will be a nice break, we'll go get McDonald's, we'll come back, we'll work in a library, and we'll go to movies. Shit.
What movie are you gonna see?
Yes.
Oh, cool. I'm gonna wait till that comes out on HBO or something.
It too?
Yeah.
I like scary movies in theaters, it's a little more scary because it's much more loud.
And you can't sit there and look at the.
Oh, you have a question? Oh.
Oh, no, I was just.
I also really wanted to see the movie
I was seeing that
Hustlers
one.
with Jennifer Lopez and Cardi B. Yeah, badass stripper bitches.
We'll pick up here on Monday.
Okay. Food, lab, movies. Oh.
You okay?
I'm doing okay.
Food, lab, movies. I don't know. Maybe it sounds better than gym, tan, laundry.
I gym tan laundry this morning. And that's why my legs feel
What
like
gym?
I'm carrying bricks right now.
Which-
Hills is not very choice.
Which gym do you go to?
The school gym.
Okay. Now
Yeah,
it's
it's right there and it's free and
for you, it's free.
they don't.
Faculty doesn't get free.
Faculty doesn't get free.
It's $25 a semester. It's nothing.
I don't know. I still feel like I would feel weird if I saw my teacher working out in my gym.
Doesn't one of the teachers teach a weight training class or something?
Yeah, the weight, those weights there suck though. The bench is too. It's not steady,
Yeah.
and like
Yeah, I go to Planet Fitness, they don't have a bench.
I'm a
24 hour.
runner. I go and I run my mile on the treadmill and then I will squat.
I hate running that treadmill.
You know, it's crazy. In high school, we had to run a